Okay, today we're going to continue looking at the apparent Earth curvature in different examples. And today we're going to be watching a video or scrolling through the frames of a video and analyzing what is happening to the light coming from the object as the object moves away. Because usually when you're looking at examples of Earth curvature, you're looking at images. I've seen, several videos, but this is a very, very high quality video, and it watches it through the entire process, and you can watch what's happening with that boat. It's not a series of images, it's a video that watches it all the way out. And you get different effects on the horizon, right? You don't get the boat rising above the horizon every time like what we're seeing in this video. So the atmosphere is variable, and if you look here, if we zoom in, you can't see anything on the horizon. I mean, there's absolutely nothing there. There are no boats. There's nothing. And so optically, we wouldn't be able to see anything with our eyes. So the boat is such a small angular size that we cannot even see it with our own optics, right? We've got to use a camera. And what I want you to notice, you see that white line right above the surface of the water? That is one of two things. Either that is the water in the distance, or that is the lower level of the atmosphere and the mist layer right above the water. And above the water especially, that mist layer is really defined. And what I mean by that is the densest layer of the atmosphere where all of the density is. On the surface, it's going to be the most dense. But we're looking at this line from many, many miles away. Okay, we can't see the boats. All of the boats are falling within that line. And I think we're looking at the atmosphere. So we're looking at that lowest level, and everything inside that lowest level, that's when we're getting all of the distortion. That's when we're getting the most light bending, is looking into that layer. And we saw that layer in the city of Chicago as well. That layer is visible when you kind of take a vantage point, and I would say she's 10 or 15 feet above the water. So because we can't tell the height of the observer, I'm not going to assume and say, oh, well, the ship should go behind the curvature here. We don't know the height of the observer. I don't know what kind of camera she was using. We can't determine the angular size to figure out the distance. We don't know what kind of boat it is. We don't know a lot of things. We don't know enough information to determine what should be happening as far as when it should be happening. But the fact that we're watching the video until it happens, we're going to be able to observe what's happening, what is happening to the light as it's happening. And think about it step by step when we're thinking about refraction. If downward refraction is hitting my eye, what's going to happen to the object in the distance? It's going to look higher, right? So if I'm looking at an object in the distance and I'm experiencing downward refraction, either on a flat earth or on a globe, that object is going to look a little bit higher. But what happens when the light coming from the bottom of the object, if the ground is flat, hits the ground over distance? Where does that light go? That light doesn't go into my eye, it hits the ground. And if it's hitting the ground before it gets to me, it's not ever entering my eye. And again, we discussed how photons are leaving the surface in every direction. But when we consider the angle of the photon above that parallel line above the surface, that angle matters when we're considering refraction and how much light is going to bend. And if we're going to apply downward refraction, we're not going to apply it as much at the upward angle as we are at the angle towards the surface, because the air is denser at the surface. So the refraction coefficient changes based on the angle of those photons coming towards the observer. And what I believe is we're seeing both types of refraction. We're seeing downward refraction from the light coming towards our eyes, and upward refraction from the horizon itself. So anything that's actually at a negative angle below my line of sight, if I'm looking at the horizon over water from 3 miles away on a globe, technically it should be 0.04 degrees. So that's the drop in front of me. If I'm standing on the ground as a 6-foot tall observer looking at the horizon from 3 miles away, that drop should be about 0.04 degrees, which unless you have equipment, you're not going to be able to really measure that. But is that drop caused by the atmosphere obscuring that lowest level and making the land invisible higher up? Or is it because the Earth is curving? Or is it because of upward refraction? And I think upward refraction combined with the atmosphere explains perfectly every observation we make. And it doesn't at all explain it on a globe when we really look at what we're viewing here. So again, nothing on the horizon. We're going to zoom in. Okay, and I want you to notice the reason I love this video from Empathy Princess. She was the original one to do it on YouTube. I can't find her channel with this video on it, but I did find the video, and I wanted to share it because she thought to proportion the boat before we watched it move away. And again, the boat is already really far away, right? We're zoomed in, and the boat is already well beyond the visible layer that we can see, and we can see that the boat is clearly above the water. If you look at the pink line represents where the water line is, where the water line should be. So either this is a mirage. The only thing this could be on a globe is a mirage. And you could kind of look at it either or from a picture. Because on a picture, if I'm taking a picture of a static moment and that effect is happening, I'm not watching that boat move away. Right? But if that effect is happening at this moment with refraction, we should immediately see the boat, as far as the boat itself, start to sink below that water line. But what we're going to see is we're going to see the bottom of the boat rise up and the top of the boat sink down as the boat gets smaller in angular size, and we're going to see that water line continue to rise. So the angular size of the ship is getting smaller, but the bottom of the ship continues to rise above the surface. Pay attention to where the water line is now. Pay attention to the proportions of the boat. And we're going to move forward in time. And you can see all of the other boats that are moving around this. Look at the distortion. Look at that boat in the distance that's even further away. The light is bending so much that it's bending the boat back into itself. Right? I mean, look at that. That's crazy looking. But because this ship is headed away and it's not moving across the horizon, we're going to be able to watch this go behind the apparent curvature of Earth. But what's happened so far? That hull is rising. The angular size is smaller than it was. We're 3 minutes or 2 more minutes into this, and the boat is moving really fast. And I'm going to link to the original video in the comments. But if you watch the boat that's moving, it's moving very fast against the background boats. So it's not just sitting still, right? It's moving away, and as it's moving away, the bottom part of the boat is rising up, the top part of the boat is compressing down, and you see that reflection below where the water line is. So why are we seeing the reflection? Well, because if the light is refracting up from the horizon at a shallow angle, and the light is refracting down from the boat, the horizon is dropping. But the bottom part of that boat is eventually going to start to disappear because the light is going to be hitting the ground before it hits my eye. And when that starts to happen, you'll see why you get that stretching effect, because that is the last bit of light that we see, right? And what's happening is that light is stretching because of refraction, downward refraction and upward refraction towards the surface. And you see this in every example of Earth curvature. And if you don't see this, you're going to see the boat rise above the surface. And we're eventually going to see that with this. But the reason why this destroys the globe is because if this is refraction pushing this boat above the horizon, and it's continuing to rise, because on a globe, you're down and away in every direction from the minute you leave, right? You're not going to be rising up, especially at this distance, you're not going to be rising up. And if you're going to say, well, this is a picture of refraction, that boat is behind the curvature, and we're seeing it above the curvature because the light is bending over the surface and it's hitting my eye, and that's why it looks the way that it does. And that's a good argument looking at a picture, like I said, but we looked at another picture a couple of minutes ago, and we watched the boat move away by a couple of minutes, and the boat is still rising above the horizon. Now, the bottom part of the boat we're going to see is going to disappear, but the overall structure is going to continue to rise as it moves away. So look at the proportions. once again.
With the mast representing 1/3.
So if we look at the proportions, if you look at the bottom 1/3, again, the hull and the bottom part of the bridge is the second third, and then you have the mast at the top. So the entire boat, it's being compressed, it's getting smaller, the angular size is getting smaller, but the entire boat is above the horizon. Again, we're 6 minutes, 20 seconds into it, and the boat is moving away. Look how fast it's moving away. But another feature I wanted to point out here is, do you see the life raft on the side of the boat? That life raft is also being pulled all the way down to the water. Do you see that? But the reason why I wanted to show that is because here in a couple of frames, watch that life raft disappear into the atmosphere. Boom, it's gone. That life raft has completely, it didn't go behind the curvature of Earth, it disappeared because you're looking through the thickest layer of the atmosphere. Now, look at how the boat is really starting to distort. The hull is being pulled up, the mast is kind of bent a little bit, it looks like, and the mast is starting to stretch out a little bit. And you can actually, not in this frame, but if we go forward a little bit, you can see the mast start to stretch out more and more as the bottom part, finally, the bottom part of that boat, the light coming from it starts to hit the ground. And it's hitting the ground in front of us. So now what do we see? We see the bridge, right? That's the bridge and the mast. But if we look at the angular size and we look at the size of the boat above the water, it's the same size that it was, right? But because the light is hitting the ground over distance, the bottom part of that, it's not going to be visible. So what's it doing now? It's stretching the bridge down to the water because the light from the hull is no longer hitting our eyes. And now we're 13 minutes into the video. And if we continue, what I want you to see here, this is fascinating, is look at how the boat now is beginning to rise above. The mast, again, it's increasing in size. The boat is not decreasing in angular size at all other than distance. The angular size is the same. And if this was going behind the curvature of Earth, the angular size wouldn't stick to what it should be above the surface. But again, we're seeing the top of the mast where it is. And the top of the mast is spread out. Now the top of the mast is covering like half of the ship. And now, because the light coming from a distance is hitting the ground, not hitting our eyes, the entire top of the bridge is being stretched down. You can't even see the separation line on the bridge anymore. So the entire top of the bridge is being stretched down. You have the original size of the boat clearly seen. And as we move forward, look at it now. Now the entire bottom part of the boat has disappeared into the atmosphere, into that lowest level. And if you look at the mast really closely, the light from the mast, now we only see the very top of the bridge. You can see the little house that they go into. You can even see the sloped roof, right? And that light, because again, the light from the lower part of the object, it's getting further away. That light is now hitting the ground, but the mast is still where it is. The angular size is still where it is. We're not watching anything sink. Watch this. What the heck? The entire boat behind the curvature of Earth, but all of a sudden, the mast, hold on. Look at that. All of a sudden, the mast is now the size of the boat. Because again, that is being stretched down to the surface. That light from the boat, that light is the only light that's hitting our eyes. So I think this evidence and all evidence that we're going to be looking at really points to the fact that Earth curvature visually is all based on distortion of light. And it's not real. And the only thing you have to do to determine this is the last thing I'm going to say, and then I'll get off of here. I don't know if I'll make another video today. Probably not this weekend, but definitely back to it on Monday. But again, as we look at this, it's going to become very clear that what we're seeing is not what we should be seeing. And when you look at the clouds, in the distance, all you have to do is get on radar. right? If you see a line of thunderstorms to the west or to the east in the morning, at sunset, you can see a lot further because you have those longer rays of light, and especially if the sun is backlighting the thunderstorm. But look how far away the line of thunderstorms is. And then look at the line of thunderstorms on the horizon and see if you can see any curvature from edge to edge. Because you can measure that, right? Over 300 miles, if I'm looking at a 300-mile line of thunderstorms from edge to edge and it's 150 miles away from me, how much curvature should I see in that line based on math, right? How many degrees are in a mile, or how many miles are in a degree? It's really simple. I mean, it's not hard to figure out how much curvature you should see. How much curvature should you see from 40,000 feet in a plane? Over 180 degrees on the horizon. And from a plane, it does kind of make the horizon look curved because of the windows. It's like the hill effect when you're driving down the road in your car. If you're driving on land, because of the land, it makes the sky kind of look curved. It's not until you get out on the water. But another thing, look at the size of the waves compared to the size of the boat when it gets small. That's another thing that will obscure the bottom part of an object when we're considering the angular size, is the wave action happening on top of the water. So I'll see you guys in the next video.